Section 7.1, graphing exponential growth functions. This is the beginning of our second half here. Chapter 7, we've been in the first half of the book, we were looking at linear functions, quadratic functions, polynomial functions, and we're going to take a look at some other parent functions as we make our way through the second half. This is the first of those groups. So, exponential functions, what this means is we are taking some base value b, we are raising it to some power value x, and these graphs, or these equations generate these graphs that kind of look like, there's two ways to think about it. You got an airplane taking off or an airplane landing, depending on if it's growth or decay, or you think about it like a skateboard ramp. We're going to focus on the growth part today, and in order for a function to be exponential growth, first of all, we're going to have a power. There's our unknown, our power there. But also, we want to make sure that with regards to the a and the b value, so the b is the base of this power, and the b value must be greater than 0 for us to have an exponential growth. With regards to the a value, that's our initial amount of something. Again, for exponential growth, we're going to focus on our a values being positive. So a's are going to be greater than or equal. Well, not or equal to, because we can't be equal to 0 there. Then we just have a constant. But our a needs to be greater than 0, or just think of that as being positive. So we have our generic function y equal abx, and if there's any function that we memorize for exponential growth, it would just be, I would say, just focus on that one right there, because when we start talking about compounding functions and things along those lines, if you just remember the a b to the x function, you'll know that b represents this thing called a growth factor, and that growth factor somehow, compounding problems might be related to some rate of growth. And we can derive the growth factor or derive these other forms that we're going to see throughout this chapter simply from y equal abx. So that's what I would focus on there, is that y equal abx form for our exponential growth. All right, we took a look at today how we were given the scenario of you're going to go and be employed by a company and they're going to pay you 1 penny the first day. And for 30 consecutive days, they are going to double the amount that they pay you each day. So day 2, you'd make 2 cents. Day 3, you'd make 4 cents. At day 4, you would make 8 cents, and so on and so on and so on. Would you work for that company? If you assume that you're going to work for 30 days straight from 8 to 5, no breaks in terms of holidays or time off. Would you work for that company? And that was the scenario we gave ourselves today. And we looked at what that generated in terms of a graph, and we tried to come up with the equation. So we're going to talk again about parent functions and introducing the parent function for an exponential. So a generic exponential parent function here we have in function notation that f of x is equal to b to the x power. Now, we just talked about this function, ab to the x power. This a value, again, is just our initial amount, or what we learned about as our vertical stretch factor when we were talking about this way back at the beginning of Algebra 2. We were introducing parent functions for our review chapter. So we're going to graph these movements that we get for this parent function off of f of x equal b to the x power. And again, we're talking about a growth, and so our b value must be greater than 0. All right. Within these functions, we are introduced to this new thing called an asymptote. And an asymptote is a line, either vertical or horizontal, and in this case, it's a horizontal line, that our graph will approach more and more closely. And in some cases, as in the case with horizontal asymptotes, your graph can actually punch through the asymptote but then reapproach it. Or in a vertical asymptote case, which we'll get to when we talk about logarithms, we won't be crossing the vertical asymptote. There are other types of asymptotes or oblique asymptotes as well, but we won't be getting into those right now. So, asymptote, a line that your graph approaches more and more closely. And yes, we do need to make sure we include the line, which is again that dashed green line there, when we graph our exponential functions. All right, domain and range. Again, going back into this stuff. So our domain is all real numbers. Every value of x works. Our range, however, is going to simply either be greater than your asymptote value or less than your asymptote value, depending on if your graph is opening up or down. All right, here we go. Critical movements for our parent function. Now, these functions, unlike the ones we've seen before, have imaginary start points. And that means that your graph does not go through them. Graph does not go through imaginary start points. These points are where we take our movements from. So the starting point is where movements, critical movements, come from, where they originate. All right. So there we go. And we see here, we have a table here. I'm going to introduce another point, a left one. We would go up 1 over b. So there's a third value of a point we can introduce here. And there's our 3 critical movements. Now, a reminder as to movements and how they get tweaked, how do they get adjusted, and where do start points come from, and all of that stuff. We have our transformation equation. Generically speaking, we looked at this again at the very beginning of the class. We were talking about parent functions. And we had all these values. We had our vertical stretch factor. We had a horizontal stretch factor. We had a right and left shift. We had an up and down shift. Well, we're going to carry those same concepts into the discussion on exponential functions as well. And what's unique about our exponential functions is this imaginary start point here, negative c. Remember, we'd always talk about taking the opposite of c. If it was an x plus a 4, it actually meant the left 4. So we're going to take a look at our imaginary start point, and the d value is unique because the d value tells you where your horizontal asymptote is going to occur. So once we know where that d is, I know I can draw a horizontal line at that value of y. Okay, so let's practice some of these. Here we have our y equal phi to the x. And I would say get in the habit of identifying your vertical stretch factors, your left and right translation, your up and down translation. We're not going to introduce any horizontal stretch factors in here. So in this case, I have a vertical stretch factor that doesn't exist. This is actually your b, which again is called your growth factor. So very generic with this one. So if I take a look at my parent function movements for this, we go left 1, we go 1 over b. We don't move at all left or right, we go up 1. We move to the right 1, we move up b. Well, in this case, these all become 1/5, 1, and 5. So those are now my movements. I notice too, there is no, so if I'm thinking about my starting point, negative CD, well that's 0, 0. And this tells me my horizontal asymptote is y equals 0. So I can go ahead and begin maybe by putting in our horizontal asymptote in there. Let's graph this thing. Here's y equal 5 to the x power. I'm going to put the horizontal asymptote in there, which is y equals 0, right there. Oh, I got a little something here. All right, well, let's just check our points and check our movement. So if we're going to move everything from our imaginary starting point 0, 0, let's see if we went left 1 and up a 5th. Yeah, that's right about there. It's got to be, estimating where some of these are. And then we don't move at all, right, left, but we move up 1. And then we move right 1 and move up 5. We can see that the movements there help us create our graph. Now, these smooth curves that these exponential functions create, as I approach that asymptote value, you can just kind of get it really right next to the asymptote itself, and just put an arrowhead on the end of it, indicating that it just keeps going on forever in that particular direction. But there's our airplane taking off, or our skate ramp. And there's y equal 5 to the x power. So we need to include all of those components when we're graphing these exponential functions. Again, as always, pause and practice, and then you can come in and check as we're working our way through these problems. We're going to start out without any vertical stretch factors or horizontal vertical translations, just doing generic stuff first of all. So once again, B2, and just get in the habit. As we develop this more and more, we're going to be comfortable. 1 over B, 1 and B, so this becomes 1 half, 1, 2 are our new movements here for this particular function. And again, opposite of CD is our start point, and there is no C and D value. So our horizontal asymptote one more time is y equals E. We'll put our asymptote in there right on that horizontal line. Come in and put our graph in here. And there's y equal 2 to the x. Again, you can see the coordinates there from our movements from 0, 0. All right, well, let's introduce a new component to our transformation equation, and that would be, in this case, this value here, and this value is our A value. So this is our vertical stretch factor. And then we remember if A was greater than 1, we were vertically stretching, and if our A was less than 1, we were shrinking. And in this case, we're less than 1, so we're going to be shrinking this graph. The 3 that's being raised to the power, again, that's just my B value. And in terms of where am I starting? Once again, 0, 0. So I know that the D tells me my horizontal asymptote is y equals 0. So we go ahead and we do our points now. We're going to be adjusting our parent function a little bit. So -1, 0, 1. I'm going to go ahead and use the B value that we have. So I have 1/3, 1, and 3. But now, because of the 1/3 value that we have out there as our A, we're going to have to multiply all these by 1/3. And our new points become 1/9 and 1/3 and 1. So now these are my critical movements that I will have for my graph. If we graph that guy, there we are. Horizontal asymptote one more time at y equal 0. I think I kind of got it moved up a little bit, so let's bring it down. Y equals 0 there. So this graph shrunk vertically. It's kind of hard to see the shrink, but again, if I compared to my parent function, for example, I would have been going through here, right? The value of y equals 3 to the x would have gone there, and then my graph would have just looked something like that. That would have been y equal 3 to the x as a comparison for what we did with the 1/3 we shrunk it. And here we introduce ourselves with a negative in front. So again, this tells me that my A value is -1. Once again, B, this time fractional. All right. Still bigger than 1, so I still have growth going on. -1. Now, 1 over B in this case. So I have a 1 over B, which is a 1 over 7 halves, which is a 1 times 2/7. So say we change and flip it. So I actually have 7 halves becoming now 2/7. And 0, 1, and 1, 7 halves again. But we're multiplying by -1. This graph is now flipped over the x-axis because I have a vertical reflection going on. The C and D value, still 0. So that tells me I still have my horizontal asymptote at y equals 0 then. Well, let's mix it up a little bit more. Now let's introduce ourselves to some translation vectors, some C and D values. When you look at an exponential function, the C translation part of the vector will occur with the power. So we can see we have an x plus a 2 power now. So there's my translation vector of left 2. Even though it says plus 2, x plus 2, remember means we're going to move left. And then here, my constant that I'm adding to the exponential part, the b to the something power part, is now my d value. So in this case, I actually have a little bit of everything with the exception of our horizontal stretch factor. Once again, a vertical stretch factor of 2. My growth factor is a 4. My c value, we're going to think opposite, is negative 2. And my d value is positive 1. So now my imaginary starting point, which is where all of my movements come from, is different. The negative CD value now is negative 2, 1. And once you know where your starting point is, the D part tells you what your horizontal asymptote is. All right, so now I have a horizontal asymptote at y equal 1. Well, so that's different so far. So there I am at y equal 1. If we go ahead and do my movements, critical parent movements here, left 1, 1 over 4, 0, 1, 1, 4. Now, because of this stretch factor of 2, everything multiplies by 2. And we get 1/2, and 2, and 8. And here are my movements from negative 2, 1. So we'll go ahead and hang out at negative 2, 1. There I am right there. And now we will go left 1 up 1/2. And then we will go no movement at all, up 2. And then right 1 up 8. And if we've done this correctly, get a graph that goes through those values there. Here we are. Now, in terms of the domain and range, we're forgetting to talk about domain and range on all of these, so let me back up a little bit here. Domain and range. So for this particular function on A, again, for every exponential function, because I can put any value in for x, I will always generate a real value for y. My domain is going to be all reals. Now, in terms of the range, we said that it was determined based on the horizontal asymptote. And if your graph is above the horizontal asymptote, we would be greater than. So in this case, it would be y greater than 0 for that function. This function, however, we had a horizontal asymptote where my graph was below. So domain, still the same thing. But range says, now I have all y values that are negative. So I have to say y is less than 0. So remember that for range and for range specifically, we do not ever include the 0 unless I have a translation that has occurred. So I'll never include the value of the horizontal asymptote. It cannot be equal to that value. So we can't include it. Maybe it's worth a little discussion on why I can't be 0. If I go back to this problem here, for example. There is no way for me to pick a value of x that generates 0 here. That's not possible. Well, what if you say, let's put a 0 in there? Well, 5 to 0 would make a 1. Well, let's put a negative number in there. Well, now that equals 1/5. Well, obviously a positive number doesn't work. So there's no way for me to get a value of 0. And that is why we have an asymptote there. That's That's a value of my function that I can never be equal to. And so we approach that value, continually getting closer and closer, but actually physically never becoming y equals 0. So that's the concept of the asymptote. Let's go back to these other functions. So in terms of the domain and range for this function here, again, my domain will be all reals. My range, however, is a y equal 0 or y equal 1 is my horizontal asymptote, and I am above that, so I'm going to have to say greater than 1 for my range. All right, for this next one, doing the same thing, identifying all of our pieces, vertical stretch factor, growth factor, horizontal translation, vertical translation. Imaginary starting point would then be 2, -2. My horizontal asymptote is the d value of my imaginary starting point. So in this case, y equals -2. I would just suggest identifying those parts because they help you quickly come up with where am I going to begin my movements from. And that hopefully will help you determine what your graph's going to look like. So there's where our movements are going to come from. Immediately where I know the starting point is, as I also know that that is the location of my horizontal asymptote, so I'm going to go ahead and put that in there. Now my graph is either going to be above or below this value. So take our parent functions. 1/3, 0, 1, 1, 3, stretch factor of 2. So everything gets multiplied by 2. 2/3, 2, 6. New movements, graph from 2, -2. And there's my graph. So really, this is kind of a review from what we did the very first week with regards to parent functions. It's just, it looks different because it's a different kind of function. Domain and range for this. Domain, as always, for every exponential. And range, y. 2, what am I, above it or below it? I'm above it, it's -2. So there's my range for that. So we use this to help ourselves model things, which is again what math is about. So here we have exponential growth models, and in this example, we see a new equation emerge. And we see that guy, which looks a lot like what we generically started with, y equal ab to the x. The only difference here is my x has become a t because we're talking about a time period, and my b value has become equal to this 1 plus r. And this is an important concept to grasp. That's all that b is it's a growth factor related on or dependent on some rate change that's occurring for that particular time period. And in these problems, the t represents a time period, which could be years, could be days, could be months, whatever. And the r value is a percent increase, and that's why it says plus r. Later on, when we talk about a decay, we're going to get that being 1 minus r. And so here's that concept of 1 plus r being equal to our growth factor b. Now, when we write these equations and we're going to use percentages, we're going to make sure we change r to a decimal equivalent. So we actually don't physically use, if it was a 5% r value, I won't use 5. I will make it into 0.05. So that's an important piece to remember here when we're working with this equation. We want to use an r value as a decimal equivalent. So here we have an application for this. We've got 1970, the population of Kern County, was 330,000. From the 70s to the 2000s, the growth grew. All right, now when we're doing these problems, I'm not going to say, hey, this is a growth problem or this is a decay problem. You're going to have to determine that from the language in the word problem. Well, this is obviously a growth because we're growing versus if it said I'm decreasing or depreciating. Growth, appreciation would be growth values. Depreciation, decreasing would be decay values. This is your R. So if we change that into a decimal equivalent, it's just dividing by 100, or 0.024 is the decimal equivalent for 2.4%. And then the next piece here, this is telling me what my t value is annually. And again, that can be days, years, months, but in this case, annually. All right, let's see if we can put together a exponential growth model, and then looking for some values here for parts B and C. Okay, our exponential growth model. Again, we'll get familiar with it, but generically speaking, it's coming from this. We're going to go ahead and make our y become population as a function of time is equal to some initial amount, 1 plus an r value to the t power. When we fill in or write an equation for these exponential models, I am going to fill in a value for the initial amount and for their rate, and thus simplify 1 plus r to be a growth factor. So what do I mean by that? Well, we're going to have P of t is equal to, what did we start with? We started with an initial amount of 330,000 people. And then we grew by 0.024% every year. So the final equation I will be looking for would be something like this. 1.024 to the t value. So there's my population as a function of time model for this particular example. And I forgot to highlight this, but this A is the initial amount of the substance, or whatever it is, in this case, a population that we are starting with. So all these different components for our equation. All right. So there's our equation. Now we're going to see what is the number of people in 1990. Well, what we do with that T in 1990 would actually equal 20. How did I get that? Well, we started in 1970, and we are 20 years out from 1970. So now I can actually plug in a value of T. I don't actually put the 1990 in there. I talk about the number of time periods, and there are 21-year time periods between 1970 and 1990. So now I'm going to find my answer by doing P of 20. And now raising to the 20th power here. Let's see what we get. So we're going to have 1.024 raised to the 20th power. That gives me 1.61, 1.6069. And I would, if I were you, just leave the value that's calculated in your calculator. I'm just going to show a rounded value here. That's what 1.024 to the 20th power is. And then that number gets multiplied by 330,000. And so that means, for this particular problem, in Kern County, the population after 20 years, if we were growing at a 2.4% annually, we'd have 530,000 people, 289.5 5, 5. Well, we're not going to talk about fractions of people, so we're just going to round it. And we're even probably being generous in saying that it's equal to 289. But we'll go ahead and just say, let's say there are 530,290 people, or maybe we would even round it to the nearest 100. So there's my population in Kern County in 20 years. The next part of the problem, graph and estimate the year when the population will be equal to 400,000. All right, so now it's a little different. Now I've been given my final amount. I've been given P of T is 400,000 people. And this is supposed to be equal to 330,000, 1.024 to the T value. Now I'm asking us to find the T value, and which is odd because we've never dealt with finding a variable that was a power. And when we talk about logarithms, we'll get into this. So one of the things that we're going to have to do right now is, well, we could simplify this a little bit. We could take our equation and do 400,000 and divide that by the 330,000. And we at least get 1.21. So this becomes 1.21 is now equal to 1.024 to the T power. And then what I could do, I guess I could just do a little trial and error, start plugging in values of T into my calculator and see what happens. Or we can graph this function and then use the graph to give my estimation of the year that the population will be 400,000. So let's do that. I have the equation actually right here, so kind of cheating a little bit, but there's my graph. Now I know it doesn't look like it's exponential just because of my scaling I had to do here, but it actually is curving right there. So I'm going to go ahead and use my graph and see it, 400,000. I know these scales are a little weird, so 400,000, here I'm going to change this, make this go by 1,000s instead of that helped. Oh, what happened to my properties? Oh, that's it. That's it. I want that 100,000. Okay. I don't know why it keeps doing this. Okay. So fix my scale. I go find the 400,000 mark. And it's right about, let's see, there. And we come over, we'd intersect our graph, and if I was drawing nice lines, I'd come down here. It looks like it's somewhere between 8 and 9 years. And that's how I can come up with my estimation of the year in which 400,000 people are reached. Well, if I'm between my 8th and 9th year from the year 1970, that would have been between 1978 and 1979, if I was interpreting my graph correctly. But we're going to come up with a better way later on how we can actually come up with that number. And if I were to plug into my calculator, well, let's test it. Let's try what 1.024 to the 8th power, for example, is. 1.2808. So that's pretty close to 1.201. So I can say probably 1978, somewhere in that year, is where I'll reach 400,000 people. All right, so we'll look forward to logarithms, which gives us a little easier way of calculating that. All right, compounding our interest. We compound our interest now. This is how many times a year are we going to compound That's what n represents. And we get a new equation. This guy. And again, what's my R? My R is my rate, expressed as a decimal. My year, how many times a year you compound. So for example, if I say monthly, you're compounding 12 times a year. If I say quarterly, you're compounding 4 times a year. This p-value is your initial amount, or principal. That's the money you're investing. Same thing as our initial amount. So here we have 5,000 bucks. And again, don't get too worried about this equation. It still is deriving itself from there. So we have an initial amount with a rate, and we're going to do this for 2 years, and we're compounding semi-annually. So how many times semi means and a half year? So we have 2 times a year that this is compounding. Here, 12 because it's monthly. And here's what my equation will look like for each of those. A is equal to P 1 plus R over N to the NT power. All right, so in our semi-annual example, we have 0.036 twice a year, which is our N value, for 2 years. And this would give me how much money would be left in my account after this amount of time. So probably the safest thing to do is do the 0.036 divided by 2 and then add that to 1. And now raise that to the power of 4. And then take that answer times 5,500, and you have in your bank account $5,906.82. So we made over $400. And I'm going to put the little estimates here. That's a safe thing to do. What about if we compounded monthly? Well, now I have 5,500, 1 plus 0.036 over 12 times. And then 12 times 2, or 24 periods in which I'm compounding. And this is going to give me, same thing, in terms of estimating my values. Now I'm raising to the power of 24, and that's getting multiplied by 5,500, and I get 8,439. See if, let me try that again. 8 raised to the power of 24, and then, yep, 8,439.36. So you can see the more compounding periods we have, the more generous our interest is going to be here. So there's another example of an exponential function specific to the world of finance. All right, hope that was helpful.